So far, we learned how to set up the geometry of the system, set up the optimizers, set up the interactions, and also set up the quick min function that allows you to find static equilibrium at every step of the optimization, so for any given set of xi values to each particle. Now we need to go, what you are still missing is the application of the displacement and also the applications of the constraints. So in our system we have that there are three supports. We have to make sure that those three don't move. So how do we apply the imposed displacement? Well, we can skip all these comments here. We'll get back to this a bit later. And we can move here. This is the set displacement command. And this set displacement command works like this. You write set disp, so the code knows that it has to set a displacement. Then it can be a displacement in x or y direction. In our example, they are all vertical displacements, so y in all cases. Then the particle number that you want to move, the quantity by which you want to move it eventually, so the target imposed displacement, the 0.4 millimeters downward, so negative in the convention here. And then there is this that is a rate at which you want to apply the imposed displacement. Let's see these parameters a bit more in detail. Notice that it's all the same for all particles, and there are 8 particles: 885, 886, 7, 8, 9, 90, 91, 92. So let's see a bit more in detail what this is, looking at the board. So this is our beam here, and we know that we want to impose the displacement to the central fifth L/5 particles at the top. We said that this length is 120 millimeters, so 1/5 is 24 millimeters. But the particle diameter was 3 millimeters. So the particles representing the central fifth here, well, they will be L/5 over D, which is equal 8 particles. So what we must do is to pick the 4 particles just before the axis of symmetry at the top and the 4 particles just after that. And to do that, well, you have to count the particles correctly. So you have to know that the first particle here has an ID of 0 in the code, not 1, 0. Second particle is particle 1. Third particle is particle 2, etc. We know that the first row was made of 40 particles, so this last particle here will have an ID of 39. Because from 0 to 39, there are 40 particles. Then we go at the top, at the row above. So the row above starts with 40, that has 41, etc. And the last particle here will have an ID of what? Well, if these were also 40 particles, this would have an ID of 39 plus 40, 79. But actually, this odd row here, if you remember, is only made of NLX minus 1 particles. So it's made only of 39 particles. Therefore, this is not going to be 80 minus 1 because we start from 0.79, but it's going to be 78. And then we start the row above with 79, and then we go until 79 plus, so the last one is plus 40 minus 1, so it's 118. And you keep counting like this until you reach the top row. And if you do this correctly, you will find that this first particle here indeed has an ID 885, followed by 886, 7, 8, 9, 890, 891, and the last one here is 892. And this is why here we are fixing the vertical displacement from particle 885, 6, 7, 8, 9, 890, 891, 892. If you produce an output file, you can check there the idea that you fixed the correct particles. So if you open again, peeping into the future, imagine that you run the simulation and you obtain this result. Now you see that the axis of symmetry is here, so you expect to be fixing the 4 particles to the left and the 4 particles to the right. So if we were correct in our counting, this particle here should be particle 888. And indeed, if you look at this path here of the screen, when you hover the mouse on the particle just to the left of the axis of symmetry here, this is particle 888. 8, 8, 7, 6, and 5. And those to the right are 9, 8, 90, 91, and 92. So indeed, the 8 particles around the axis of symmetry from this snapshot are the 8 particles for which we fixed the displacement in the input file. So we did it right. This can be useful going back to the output file and hovering the mouse on the particles that you believe are fixed can be useful to spot if there is any error. Because then maybe you're convinced that you are fixing the right particle, but when you hover the mouse there, you see that the IDs of those that you fixed are not the IDs that you really wanted to fix. So maybe you counted incorrectly the IDs when you were doing this process that I just showed you, and so you can fix any mistake later and repeat the simulation. So this is how you find the IDs of the particle that you want, to which you want to impose a displacement. Then, as we said, the value of the imposed displacement is the 0.4 millimeters that we want to impose here to these particles at the top, 0.4 millimeters. The reference system is y going up, x going to the right, so this is a negative 0.4, and then this rate has to do with the process that I showed you in the previous video. So I said, when you want to trace the force displacement curve, you want to reach the imposed displacement of 0.4 millimeters. I'm putting it positive, but of course it's negative in this case. So what the code does is to progressively increase the displacement over time. So what it's doing is essentially a dynamic simulation, but it is highly damped. So it's a quasi-static simulation. This simulation is the quick min that we were running before, with this time increment of 0.02 seconds. But then we have to tell the code how fast do we want this u imposed to increase during the time of this simulation. So at which rate do we want to increment u to obtain the force displacement curve here, and then eventually the energy under it. And this is the rate. So this rate is in units of length divided by unit of time. So it's how many millimeters per second of displacement are you applying. So you see that we are going quite slow. We are applying 2 × 10⁻⁴ millimeters per second. Each step of the simulation where we are imposing the displacement is increasing by 0.02 seconds. So at each step we are applying a delta u equal to 2 × 10⁻⁴, the rate that we are imposing here, times 0.02, which are the seconds, which is the time step that we are using in this quasi-static simulation. So effectively we are working at 4 × 10⁻⁶ millimeters applied at each step of this quasi-static simulation. So we are applying the load very, very slowly. This is a parameter that you also have to explore with. The smaller you make this value, the more precise this curve, the more quasi-static this curve will be, but also the longer it will take to reach the imposed displacement. You will need more steps if you are applying a small displacement at each time. So the simulation will take longer and the overall optimization will take longer as well. However, if you make it too big, what happens? Well, if you make it too big, typically what happens is that you will have a non-quasi-static behavior. So instead of going along this line here, that is, let's say, the perfect quasi-static, the theoretical quasi-static, what you would get is a behavior as if the system was stiffer. So you would initially overestimate this curve here. You will overshoot it. But then what you will notice also is that the minimizer will realize that you overshot, and when you reach the imposed displacement, instead of stopping, it will actually continue relaxing until going back to the correct force displacement solution. And once it knows this position, it is able to reconstruct correctly the strain energy under the curve. So in other words, it's not too concerning if you make this too big. However, if you make it excessively too big, you may not be able to actually find the solution to this problem and the system may crash. So it is always convenient to make it not too big. So you can accept a little bit of overshoot, not too much. We will see in a later video how you can recognize whether there is such an overshoot or not, and how you can judge whether this overshoot is acceptable or whether you should probably repeat the simulation using a smaller rate and going a bit slower. So far we saw how we can set a target displacement for certain particles and let the system always try to impose the displacement as the source of deformation that allows the optimizer to judge whether the system is getting stiffer or not and redistribute the shears with its sensitivity analysis. There is also the possibility, instead of imposing displacement, to impose forces. And actually, if you look at the manuscripts that I have given you, the first manuscript is under imposed forces, the second manuscript is under imposed displacements. Well, to use imposed forces instead of imposed displacements in the code, simply you can comment out or delete all the set disp commands and instead use the set force commands, which are very similar in structure, actually a bit easier, because when you set a force, you don't have to worry to progressively increment it. You just set all the force and then the system will move until it finds equilibrium. So to do this, you simply use the command set force, x or y direction, the ID of the particle to which you want to impose the force, and then the value in kilonewtons in my case, or whatever unit of force you're using with the units you've decided to use, as a last value here. So this would be imposing a force of 0.5 kilonewtons pointing downward, because it's a negative y direction, to the particle 888, which is the one just to the left of the axis of symmetry at the top. And then the same would be applying this to the particle just to the right. So the two central particles at the top of the beam would have a force of half a kilonewton pointing downward applied to them. And again, if we unset all these set displacements here, so we comment them out or we just delete them, then we would run a simulation with an imposed force. But in this example, for now, we want to work with imposed displacement, so let's comment this out again and let's keep the set displacement we saw before.